All right, let's take a look at example problem 6. A sealed rigid tank. So again, here we have our keyword, a sealed rigid tank. All right, and that signals to me that V total is constant. And since it says sealed, I'm assuming mass isn't leaving, right? So V is constant. And more importantly, okay, and we'll write this out, later. When I think of my first law of balance, delta U is equal to Q plus W, is that if I just have PV boundary work, the W is 0. All right, so that we're just going to have delta U is equal to Q. Okay, but more on that as we go through it. A sealed rigid tank of 1 meter cube capacity contains 1.2 kilograms of water at 1 bar and 99.61 degrees C. To this tank we add heat until the pressure increases to 3 bars. What is the temperature at the end of heating? Calculate the amount of vapor before and after heating, and calculate the amount of heat added. Alright, this seems like a fun one. Alright, so to start, we're told V total is equal to 1 meters cubed. Our mass is 1.2 kilograms. Pressure is 1 bar. And our temperature is 99.61 degrees C. Okay. So here's our initial state. Okay, and then in our final state, we're going to have a pressure of 3 bars. Okay. Before I do that, though, I'm going to go to my steam tables, and I want to know at 1 bar and 99.61 degrees C, what do we have? So we were in the superheated steam tables last time. I guess let me go back to the superheated steam table since those are incremented in bars. Okay, so at 1 bar, saturation temperature is 99.61 degrees. Okay, so I have a system at two-phase coexistence, right? So I have a system at vapor-liquid coexistence. Great. Okay, so what does that tell me? Well, so if I'm at 1 bar and 99.61 degrees C, I have that the specific volume of my vapor phase is 1.694. Okay, and that's going to be meters cubed per kilogram. Okay, specific volume of my liquid, that's 0.00104. So 0.00104 meters cubed per kilogram. Okay. Now, since I'm at two-phase coexistence, right, I'll assume I'll have some vapor. So the vapor would expand to fill the tank. So the specific volume of my tank, right, so is going to be, meters cubed per kilogram. Perfect. They gave us the correct units. It would be 1 divided by 1.2 meters cubed per kilogram, which is equal to 0.83333. So my volume is 0.8333 meters cubed per kilogram. Right, and perfect, right, the volume's between that of my vapor and that of my liquid. So if I'm thinking in terms of my PV phase diagram, I'm under the dome. I've got two-phase coexistence. Perfect. All right, so I'm going to add, all right, a subscript 1 to P, T, and then V here, right, just as I think about, my process. Because now what's going to happen, okay, is in my final state, and actually let me just put a 1 on all of those, right, so I keep track of things. So my final state, to this tank we add heat until the pressure increases to 3 bars. what is the temperature at the end of this heating? Okay, so we're going to increase the pressure. We're going to add heat, all right, till the pressure increases to 10 bars. All right, pressure increases to 3 bars. Okay. Okay, and we have a sealed rigid tank, so my specific volume is going to be the same as I had in state A. Right, this is the specific volume of my system, not the liquid or vapor, but that system. Right, where I have 1.2 kilograms, right, in a total volume of 1 meter cubed. So V2 will be equal to V1, which is 0.8333 meters cubed per kilogram. All right, and the question is, what is the temperature at the end of heating? Calculate the amount of vapor before and after heating, and calculate the amount of heat added. All right, so these are all kind of, one and the same problems, right? And so we might as well, interpolate and get everything that we need at the same time. All right, and so the key is going to be, again, okay, if I kind of have an aside. So my first law of balance for this problem, all right, first law is delta U is equal to Q plus W. Okay, so we're not told anything about shaft work, so if we just assume we have PV boundary work, then that's the integral of negative P dV. But if volume's constant, right, my work is just 0, so my first law of balance is just delta U, which is U2 minus U1 is equal to Q. So if I need to find Q, right, the heat added, I need U2 and U1. Okay, so what I'm going to need to find is I'm going to need to find U1 for my state 1, right? So I'm going to need U1. Okay, and in order to get U1, in this case I'm going to need U1 vapor and U1 liquid. Okay, and so we'll compute all those. Okay. Well, so we're going to need to get, just trying to figure out where to write it. I'm going to need to get U1 liquid and U1 vapor. And then once I have U1 liquid and U1 vapor, I'm going to need to get U1. And we'll write it down later because that's going to be, U1's going to be the fraction that's liquid times U of the liquid plus the fraction that's vapor times U of the vapor, right? So essentially, we'll need to calculate the quality, which is needed for B anyways, right? So all is good. Okay, so I'll need to get that. And so let me go and look those up now just so we have them. So when I was at 1 bar, 99.61 degrees C. So U of my liquid is 417.33. 417.33. That's kilojoules per kilogram. And U1 of my vapor is 2505.5. 2505.5 kilojoules per kilogram. All right, so let's look at our final state. Okay, so first we're at 3 bars. Our specific volume is 0.83333. So I'm going to stick on my superheated steam tables. I'm hoping 3 bars is here. All right, that's perfect. So at 3 bars, at vapor liquid coexistence at 3 bars, here's VL, here's VV, it's 0.6058. So our specific volume is greater than the saturation value at 3 bars. So that's going to tell me I have a superheated vapor. Okay. So then what I'm going to do is I'm going to look in the superheated region, and I'm reading across on temperatures until I find our specific volume. So our specific volume is going to be between 250 and 300 degrees. Okay, and I know I'm going to need U2 as well. So what I'm going to do is I'm going to set up a table, and I'm going to interpolate for everything at the same time. Okay, so here's temperature. Let me get U on here in kilojoules per kilogram. And then let's get our V in meters cubed per kilogram. Okay, we'll get temperature and U at the same time. We'll get it all. At least we know this part will be easy, and that the fraction that's vapor for part 2 is going to be 100%. Okay, so that's great. So we're between 250 and 300 degrees. So that's 250. That's 300. So at 250, U is 2729.0. 2729.0. At 300, it's 2807.0. In terms of volume, at 250, it's 0.7965. And at 300, it is 0.8753. Okay, and our volume is 0.8333. Okay, so let's interpolate and find T2 and U2 at the same time. Okay, so I'm going to go over to MATLAB. I'm going to open up a script and create a vector for my temperatures, which are 250 and 300. Bam. U. Keep going. 2729.0 and 2807.0 and V 0.7965, 0.8753. Okay, and my volume is 0.8333. Okay. And I guess actually if I wanted to compute it, right, I could put in 1 divided by 1.2 here. Okay, so let's get U2. Now let's get T2. Would be interp1. So I'm going to perform linear interpolation. Okay, V is the value that I know. So do V comma T comma V. And then let's get U2. So that'd be V comma U comma V. All right. So I'm going to estimate U at that value of V. Okay, so I've got to save it. Okay, so I get T2 is 273.3714, and that's degrees C. And U2 is 2.7655 times 10 to the 3. And that's kilojoules per kilogram. Okay, so I've got my final temperature. So that's 273.3714. I know that the amount that's vapor in my final state is going to be, it's going to be all vapor. All right. And so what I need to compute then is I need to get the fraction that's vapor and liquid in my initial state, and then use that to calculate U in my initial state, and then I can calculate Q. So this would be, let me label this like x2. All right, the fraction is vapor. My final state is 1. So let's add a new page. Okay, and so let's return. So we want to calculate the fraction, liquid, and vapor in our initial state. Okay, and so the data we have is on V. So remember, the key is that V total, right, is equal to M times V, and that's going to be equal to the amount of mass in my, put a superscript liquid phase times specific volume of my liquid plus M times vapor times the specific volume of my vapor. Okay. Now, if I want to make this intensive, well, not intensive, but deal with, fractions, fraction liquid, fraction vapor, is I'll divide through by M the total mass, and I'll get that V is equal to ml over M VL plus mv over mvv. Okay, now this is just the fraction liquid and the fraction vapor. Okay, so V is going to be equal to XL VL plus XV VV. All right, then to make it complete, all right, is I know that M is just ML plus MV. So if I divide through by 1 again, or M again, I get 1 is equal to, okay, using this notation, XL plus XV. Okay. So if I'm interested in the fraction vapor, say, okay, so from here, XV is going to be 1 minus XL. Okay, or XL is 1 minus XV. So let me eliminate XL in favor of XV. So I'm going to rewrite this as V is equal to 1 minus XV times VL plus XV times VV. Okay, so if I expand out, that's VL minus XV VL plus XL VV. So V is equal to, all right, this is XL times VV minus VL plus VL. So XL then would be equal to V minus VL. And actually, this is a V here. My handwriting is just bad. And somehow that's a V. So X V is equal to V minus VL over VV minus VL. Okay. All right. So let's do it. So then X, call it 1V, fraction vapor in my initial state will be equal to, so I'm going to add up here. So let's scroll back up to our first page. It's the first page. We have that V1 vapor is equal to 1.694. V1 liquid is equal to 0.00104. Okay. And V again was equal to 1 divided by 1.2. So the fraction of in state 1 in vapor is equal to V minus V1L divided by V1V minus V1L. And then if I want the fraction in the liquid, it's 1 minus the fraction that's vapor. Okay, so the fraction vapor is 0.4240. So 0.40, and then the fraction that's liquid, that was 0.5760. All right, so then if I want U1, right, the internal energy of that system, okay, again, we're on a specific case, it would be equal to, because if I should note that we're told the mass, right? We have 1.2 kilograms. So if I wanted to, okay, I could calculate the amount of mass of liquid, amount of mass vapor, just by multiplying this by that total mass. Okay. I want to keep everything on a specific basis for now. Okay. So specific basis, I mean, you can always just multiply by mass. So U1 would be X1 L times U1L plus X1V times U1V. Okay, so let's go ahead and compute that. So I'm going to scroll up to the values and we'll go down and type those in. Alright, so we have U1L is equal to 417.33. U1V was equal to 2505.5. Okay, so therefore U1 is going to be equal to X1V times U1V plus X1L times U1L. Okay, so U is 1.3027. 1.3207, 1.3027, 3027 times 10 to the 3, and that's kilojoules per kilogram. Okay, great. So I've got fraction liquid or vapor initially. I had my final temperature. I have that we had superheated vapor after the heating process, so its fraction vapor was 1. So then to get Q was U2 minus U1. Okay, and so we have U2 up here. Okay, so to get Q then, okay, again I should ideally be making comments here throughout, but Q is U2 minus U1. So Q is 1.4627. 1.4627. 1.4627 times 10 to the 3 kilojoules per kilogram. All right, and I haven't, been mentioning signs, all right, but Q is positive, so that means it's heat added to our system. All right, so heat's being added to our system. If you wanted the extensive Q, all right, so let's call it, say, Q total. Come on. Q total would be equal to M times Q, okay, where that's 1.2 kilograms times Q. I'm pretty sure 1.2 kilograms. Okay, and that would be equal to, and so just to do it, I can even just type in here 1.2 times Q, 1.7533. 1.7553 times 10 to the 3 kilojoules. Okay. All right, that was a fun one. So there's Q. We've got fractions of liquid and vapor. And that was needed in our initial state because it's two-phase equilibrium just to be able to compute the internal energy that we had initially. All right, another one down. We'll see you in problem 7.